Greetings astronauts. Today we will talk about our AI mini project and do a little demonstration. The topic that we have chosen is reinforcement learning. Please enjoy. First of all, let me introduce you to reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment to maximize the cumulative rewards. It mimics the trial and error learning process that humans and other animals do to achieve their goals by receiving feedback like rewards and penalties for its actions and adjusting its behavior accordingly. These are components of reinforcement learning. Agent is the decision maker, environment is the system, state is the condition the agent currently in. Rewards is the feedback, and action is the possible moves that agent can make. These figures show how the reinforcement learning works. When the agent makes an action to the environment will return the state and the rewards to the agent. So there are two types of reinforcement learning. The first one is model-free, where the agent learns directly from its experience. The example for model-free reinforcement learning are Q-learning and deep Q-learning or DQN. And the second one is model-based reinforcement learning, where the agent builds a model to plan and predict the optimal path. For example, DynaQ learns a model from experience and uses that to provide more model transitions to a value function. This time we will only discuss about the model-free ones, which are Q-learning and deep Q-learning. What is Q-learning? As I mentioned before, Q-learning is a model-free algorithm. It teaches an agent how to act in an unknown environment. In order to maximize rewards over time, it uses the adaptation of the Bellman's equation to find its Q value. The Q value represents the expected future rewards an agent can receive. To keep track of this value, we use Q table, which is a table that maps states and action pairs to their Q values. The Q value is updated using this equation. But what if the values are more complex? As you can see in Q-learning, we use Q table to update the Q value. However, the table cannot handle the large state space. It will require a lot of memory and more cost. Imagine a game with 1000 states and 1000 actions per state. We will need a table of 1 million cells. So the deep Q-learning is introduced. In deep Q-learning, we use the Q network to update the Q value. You can see it in the figure on the right. Instead of mapping a state and action pairs to a Q value, the neural network maps input state to the action and Q value pairs. To implement Q learning using DQN, we modify the Bellman equation with the theta elements. Then the loss function can be created. Using gradient descent, we minimize the loss function to essentially train the model. Next, we will show you the demonstration of deep Q-learning lunar landing.
Let's have a look at this project where we try to land our lander in Moon. We see that the states are continuously changing, which is too much for a lookup table. We have sensor inputs that says horizontal and vertical positions with their velocity and angle, as well as sensors that detect left leg contact and right leg contact. So when you put all of this together, it is very hard to quantify the number of states. However, the actions are very few. The lander can either do nothing, fire the main engine, or either left or right engine. Our goal is to land properly as fast as possible, consuming less fuel. And in order to do that, we have this loss function which we are going to minimize using gradient descent. That's how we're gonna process the neural network. And for reward, we have plus 100 to 140 points to land on 0 speed, that means without collision, plus 10 points for each leg contact, and we decrease point to optimize for less fuel consumption, and if the lander crashes, we have minus 100 points. We implement neural net using PyTorch. We have 3 layers of 64 neurons each, and third layer comes to give raw Q value output, and we can tune the size of neural network and the learning rate. And for the agent part, it can act in the environment, so that means it can perform those 4 actions, and using the replay memory they can learn so that in next replay it can perform better action. And when we perform the training, as you can see, it was quite fast and crash landed. That means for the initial testing, like initial episodes, we have average score of 93, which gradually improves up to 200. So this is our baseline, and the environment is solved using 200 episodes. And now let's enjoy the remaining episodes, which is progressively better because the loss function is minimized and the agent learns to consume less energy and land as properly as possible based on these reward functions. Here are the examples for episode 50, which never landed, and for the episode 100 it was quite well, but average score is still minus 93, so there is a lot of work to do. These are the performance for episode 200 and 300 each. Landing was stable enough, but they still consume a lot of fuel compared to the previous crash landings. So all we can do is optimize the learning rate and the size of neural network to see if there are enough neurons to form a pattern, or we need more episodes to train them. Finally, coming to conclusion, which is last episode, we have stable reward around 200 points, and as you can see, the rocket lands properly in a checkpoint, consuming least fuel. Coming to conclusion, we explore what reinforcement learning is. We see how Q learning works. We compared Q table versus neural network and the different scenarios they can be used, and I present the example for continuous spaces. And the limitation of this compared to Q table is that we have to train for a lot of episodes. This was quite a good example that requires few episodes, but if it was like real world environment training on real robots, it could be more than 10,000 episodes and a lot of GPUs. You can find my code in that link or scan the QR code. Thank you very much for being with us. Have a nice day.